Hello, welcome back. Today we're going to talk about counting permutations. Let's start off with a thought question. In how many ways can we arrange the letters A, B, and C? We can write A, B, C. We can write A, C, B. We can write B, A, C. We can write B, C, A. And we can write C, A, B, and C, B, A. For a total of 6 arrangements. Now, one of the guiding ideas in combinatorics is that we'd like to count these arrangements, but without listing them. We're developing techniques to be able to do that. We'll be wanting to apply the multiplicative principle that we learned last time. We'll be thinking of these arrangements as a first letter, a second letter, and a third letter. We'll think about each of the positions individually. So how many choices are there for the first letter? There's 3 letters in this set, so there's 3 choices for the first letter. No matter what letter we chose in the first position, for example C, there are going to be 2 more choices left for the second letter. And then, no matter what letter we chose first and second, there will always be 1 choice left to fill out our arrangement. We now apply the multiplicative principle that says that there will be 3 times 2 times 1 total ways to arrange these letters, which is the same number that we had from above. When we arrange objects in an order, that's called a permutation. We can also say that we are permuting the objects. The general rule is that if S is a set of n distinct objects, the number of permutations of S is n factorial, n choices for the first one, n minus 1 choices for the second one, n minus 2 choices for the third one, etc., and 1 choice for the last object. Let's try an example. Let's say you go to your favorite fast food restaurant and they have 10 items for sale. In how many ways can you order the menu items if you always put French fries at the top of the list? You'll be writing a list, and you'll have French fries at the top of the list, and then you'll order the rest of the items below. So there's 10 total items, but the position of one of them is already fixed. So in effect, we're actually ordering 9 items for the rest of the items in the list. So since this is a permutation of 9 items, the answer is 9 factorial. Now, sometimes you do not want to order all of the objects in the set. If instead you only want to order k objects out of n, this is called a k-permutation. Let's look at a fun example. In this year's mayor's race in Fruitville, there are 9 candidates. We've got apple, banana, cherry, and then mango, nectarine, orange, pear, raspberry, and strawberry. We go to the voters to decide which candidate they want to be mayor, and voters are asked to rank 4 candidates on their ranked choice voting ballot. An example of what this looks like is the ranking that this voter gave, where the first choice candidate was cherry, the second choice candidate was strawberry, the third choice candidate was banana, and the fourth choice candidate was orange. A voter has 9 choices for the first ranking. The candidate they rank second can be any candidate except the first candidate. The candidate they rank third can be anybody except the first 2 candidates. And the fourth place candidate can be anyone except the first 3 candidates. So there are 9 choices for ranking the first candidate, 8 choices for ranking the second candidate, 7 choices for ranking the third candidate, and 6 choices for ranking the fourth candidate. By the multiplicative principle, we have 9 times 8 times 7 times 6. I do want to highlight something that can be confusing. Notice that we have 4 candidates that we have to rank, and because of this, we're multiplying 4 numbers together. The first number is n, the second number is n minus 1, but because there are 4 numbers here, and the numbers start with 9 minus 0, the last number will be 9 minus 3. Or 9 minus 4 plus 1. So even though there are 4 numbers, this last number is 9 minus 3 and not 9 minus 4. So let's come up with a general formula for these objects. We have a set of n distinct objects, and we're looking for k permutations of s. So we're multiplying k numbers together, n times n minus 1, down to n minus k plus 1. That's the formula we saw on the previous page. Now, there's another way to write this product in a nice compact form. If we take our product, and if we multiply by n minus k times n minus k minus 1, dot 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 down to 2 times 1, in a numerator and a denominator, so we're multiplying by 1, you'll notice that the numerator is the same as n factorial, because it's a product starting at n, then times n minus 1, times n minus 2, all the way down to 1, and the denominator is also a factorial. It's n minus k factorial. This value occurs repeatedly in counting questions, so we've invented a notation to represent this quantity. We'll write as p of n comma k. You may have also seen a notation like this, n following factorial k, or npk. We will be using p of nk. On the previous page, we were ranking mayoral candidates. There were 9 total candidates, of which we needed to rank 4 of them, and so we would use the notation p of 9, 4. That's it for now. See you soon.